this problem here, we have these forces acting on Porky Pig, and we want to ultimately determine the horizontal and vertical acceleration of Porky Pig, and then the overall magnitude and direction of that acceleration. But the first thing we're really going to think about, we already have our picture here, is breaking these forces into their x and y components. So I'm going to go ahead and draw those x and y components for the two angled forces. And then we can think about what the value of those components are. So this y component here is going to be 80 sine of 30. That x component is going to be 80 cosine of 30. And then for the 95 Newton one, we have 95 sine of 20. And the x component is going to be 95 cosine of 20. So that's going to be my very first step here. The next thing I'm going to do is I'm going to want to break it into max and may. Okay, so I'll start with my x direction. Some of the forces in the x direction are equal to the mass times my x acceleration. And so I'm going to think about what x forces we have. So we have that 95 cosine 20, the 80 cosine of 30, and then that 30 Newton force going the opposite way. So I can say 95 cosine of 20 plus 80 cosine of 30 minus that 30 Newton force. That's going to be equal to the mass here, which is 40, times my x acceleration. I go through and solve for the value of those forces, okay, and we end up with 89.3 plus 69.3 minus 30 equals 40 times my x acceleration. And so I find that my x acceleration here is going to be equal to 3.21 meters per second squared. Now that I have those x forces set up, I can go ahead and think about my forces that I have in the y direction. So in the y direction, we have that 20, and we have the two vertical components of those angled forces. So I can say 20 plus 80 times the sine of 30 minus 95 sine of 20 here, and that's going to be equal to my mass, which is 40, times my y acceleration. I can put in those values here, so it ends up being 20 plus 40 minus 32.5. Okay, and again, those signs really just indicate direction, because this force here is going down. It has a negative sign. All right, and the same was true in the x. That force of 30 to the left was also negative, because left is typically the negative direction. So all that is going to equal to 40 AY. So I find that my y acceleration here is 0.92 meters per second squared. So that solves my x and y acceleration. What I want to do now is put those forces together. Okay, so I'm going to draw my triangle. So I'm going to say in the x direction, I have 3.21 meters per second squared of acceleration. In the y direction, I have 0.92 meters per second squared of acceleration. And what I'm ultimately looking for is this hypotenuse here and this angle. That's going to be the overall magnitude and direction of my acceleration. So to get the value of my hypotenuse here, it's going to be a squared plus b squared equals c squared. So 3.21 squared plus 0.92 squared, and that's going to be equal to c squared. So I find that my hypotenuse here is going to be 3.34 meters per second squared. And for that angle, what I'm going to do is I'm going to say tangent of that angle is equal to the opposite side, which is 0.92, over the adjacent side, 3.21. So then my angle is going to be the inverse tangent of that fraction there, 0.92 over 3.21. And so I find that my angle here is going to be 15.9 degrees. So overall, I have a acceleration of 3.34 meters per second squared at an angle of 15.9 degrees, and that direction would be north of east. Okay. The other acceptable angle, if you did solve for the angle measured from the vertical instead of the horizontal, that angle there would be 74.1 degrees, and then it would be east of north. So that would also be an acceptable answer. All right, moving on to this problem here, we have Marvin the Martian, who has a set of forces acting on him. We'll eventually worry about what the question's asking, but the first thing I'm going to do once again is break that angled force into x and y components. So this x component here is going to be f1 cosine of theta. This y component here is going to be f1 sine of theta. Now that I have that, I can go ahead and set up my max and may, and that's going to allow me to solve for this unknown force here. That's what I'm ultimately looking for in terms of the other forces. So thinking about the forces that we have in the x direction and setting up my max here, I only have two forces. We have this F2, and we have the x component of that F1. For this problem, I'm going to say that left is the positive direction simply because that's the only direction that I have any forces. And so I'm going to say F1 cosine of theta plus F2 is equal to m times ax. And again, you can make that all negative if you would like. It doesn't really matter as long as you're consistent. What has to be true is these two forces here, this F cosine of theta and F2, have to have the exact same sign. Okay. Moving on to the y direction, the forces that I have in the y direction are going to be equal to may. So I have that unknown force, and I have this F1 sine of theta. I'm going to make up the positive direction there, so it's going to be F1 sine of theta minus F is equal to may. So for the first question, we want to find the unknown force, and we know the Martian is not accelerating vertically. That means that that y acceleration is 0, and I can just say that F1 sine of theta is equal to F, that unknown force. So there's the answer to my first question. Second question, we want to know what is the acceleration of the Martian in terms of F1, F2, theta, and m. So here we're really looking for our horizontal acceleration because we know we're not accelerating vertically. So we're just trying to solve for this ax. So all we really have to do here is divide by m, and it's going to end up being F1 cosine of theta plus F2 divided by m is equal to our x acceleration. All right, moving on to this next one here. This one's all about gymnastics and the iron cross, which is a position on the rings in gymnastics where the gymnast basically supports themselves using their arms, just holding onto the rings. It's considered to be a very, very difficult position to do in gymnastics. So we're going to look at the physics of that for a second. So we're going to basically treat this and model this system as a box or an object with two ropes where the ropes represent the two arms. All right. So the first thing we want to do is we want to draw the forces acting on this object, on the box, which represents the person. So I'm going to go ahead here and draw it down here just so I have a little bit more space. The first force we have is the force of the earth, which I'm just going to label as Fe, and that's actually what the problem defines it as. We then have the force from rope 1, I'll call that F1, and the force from rope 2, which I will call F2, and both of them are pulling here at an angle of theta relative to the horizontal. So there we have this first part of the question that just asks for the free body diagram showing the forces acting on the object. For the second part of this problem, we want to derive an expression for the force from one of the ropes in terms of Fe and the angle. Okay, so two things I'm going to do here. First of all, I'm going to break these angled forces into x and y components. All right. The other thing I'm going to do is I'm going to recognize that these two ropes are identical and they pull at the same angle. Because they pull at the same angle, right, the x components have to be equal to balance the object, and therefore the y components are also equal, and thus these two forces are actually the same. So rather than calling them F2 and F1, I'm just going to call each one of them F, because this justifies why the forces are the same. So what we're going to do now is we're going to go ahead and set up our max and our may. And so first I'm going to set up my x forces. And what I find with that is in the x direction we have the two horizontal components of that angled force. Okay, nothing from Fe. And so that ends up being F cosine of theta minus F cosine of theta. And that's going to be equal to our mass times our x acceleration, which is 0. You might recognize that this side of the equation ends up being 0, as does that side. So this equation doesn't really tell us much. This just verifies that those two x components have to be the same. In the y direction, all right, we're going to be able to get some more useful information and actually solve for that force. So in the y direction, we have the vertical components, F sine of theta and F sine of theta. And so that equation ends up being F sine of theta plus F sine of theta minus Fe, and that's going to be equal to our mass times our y acceleration. But if we're just hanging there, performing this iron cross, not moving at all, our y acceleration is just 0. And so what we get, combining those two terms, is 2F sine of theta minus Fe equals 0. And that means that 2F sine of theta is equal to Fe. And so we solve for that force, it's going to be Fe divided by 2 times the sine of theta. And so there's my expression for the force of tension in one of the ropes. So part C here asks us why it's physically impossible, right, to have the ropes be completely horizontal. And so for that one, I'd really think about two things. We can look at our equations here, but I really think the diagram's your most useful tool here. We need to have all of our forces balanced. We have that downward force of Earth, and that means, all right, that we have to have a vertical force, all right, going up to balance that downward force of Earth. If we have the ropes completely horizontal, that's simply going to mean that there is no upward vertical force, and it would be impossible to have balance forces allowing this object to be at rest. We have to have some angle, all right, to create that upward force to balance out the force of Earth.